How long would it take a human being to reach the edge of the solar system? On the surface, this feels like a question with a clean, calculable answer. You find the edge, you measure the distance, you divide by speed, and you arrive at a number. Simple arithmetic applied to a simple geography problem. Except the solar system does not work that way, and neither does human space travel. And once you start pulling on those two threads simultaneously, the entire question unravels into something far more complex and far more fascinating than it first appears. The first complication arrives before you even calculate a single number. Ask 10 astronomers where the solar system ends, and you will receive answers that differ by hundreds of billions of miles. Some will point to the orbit of Neptune, the outermost recognized planet, sitting roughly 2.8 billion miles from the Sun. Others will draw the boundary at the heliopause, where the Sun's solar wind finally surrenders to the pressure of interstellar space, a bubble edge located somewhere around 11 billion miles out. Still others will insist the true boundary lies at the outer edge of the Oort cloud, a frozen shell of ancient comets extending nearly 9 trillion miles from the Sun, the absolute limit of our star's gravitational reach. Each answer is defensible. Each answer is also radically different, and each one produces a completely different journey time when you start doing the math. The second complication is the one that this video is fundamentally about. Robotic probes can endure conditions that would kill any human passenger within hours. They require no food, no water, no breathable atmosphere, and no protection from the radiation environment of deep space. When Voyager 1 crossed into interstellar space after 35 years of travel, there was nobody aboard suffering from bone density loss, muscle atrophy, psychological breakdown, or radiation poisoning. A human journey changes every single variable in the calculation. The spacecraft grows heavier with life support systems. The mission demands reliable fuel supplies for deceleration, not just acceleration. The crew requires shielding against cosmic rays that would otherwise deliver lethal doses over years of exposure, and the timeline becomes constrained by biology in a way that no robotic mission ever faces. Machines can wait, humans cannot. Speed matters, but it is only one dimension of the problem. The choice of destination reshapes the answer entirely. The engineering required to keep human bodies alive across decades of travel introduces constraints that dwarf the propulsion challenge on its own. Radiation accumulation, fuel mass, the need to actually stop rather than simply fly past, and the psychological reality of spending years or decades inside a sealed vessel all combine to produce an answer that shifts dramatically depending on which assumptions you allow yourself to make. What follows is an honest accounting of that answer under several different definitions of where the edge actually sits. Not a science fiction estimate built on technologies that exist only in theory, but a grounded examination of what current and near-future capabilities actually permit, what the human body actually tolerates, and what the physics of the journey actually demands. We will travel from the inner boundaries of the solar system outward, past the familiar planets, through the scattered debris fields of the outer system, across the heliopause where interstellar space technically begins, and finally to the Oort cloud, where the Sun's gravitational grip grows so faint that comets spend millions of years in near-perfect solitude. At each boundary, the answer to how long a human trip would take changes in ways that will surprise you. Some of those answers are sobering. At least one of them borders on the absurd. Before calculating any travel time, you need to fix a destination. And the moment you try to pin down where the solar system actually ends, you discover that the question contains a hidden assumption, that the solar system has one edge rather than several, each defined by a different physical phenomenon and each located at a profoundly different distance from the Sun. Start with what most people picture when they imagine the solar system: 8 planets orbiting a central star, arranged in a flat disk, with Neptune marking the outermost boundary. This mental image is not wrong, but it is dramatically incomplete. Neptune orbits the Sun at an average distance of roughly 2.8 billion miles. That sounds enormous, until you realise it represents only a small fraction of the space our star actually dominates. Stopping at Neptune to declare the solar system finished would be like describing a city by mapping only its downtown core and ignoring everything beyond the first ring of suburbs. The rest of the structure extends outward in layers, each defined by a different force and each marking a different kind of ending. The region immediately beyond Neptune is the Kuiper Belt, a broad band of icy debris orbiting the Sun between roughly 2.8 billion and 5 billion miles from our star. Pluto lives here. So do hundreds of thousands of smaller frozen objects left over from the formation of the solar system. The Kuiper Belt is not empty space. It is a structural feature of the outer planetary system, a population of primordial material that never coalesced into a full planet because Neptune's gravitational influence kept disrupting it. The Kuiper Belt has a reasonably well-defined inner edge where Neptune's orbit ends, and a fuzzy outer edge where the population thins dramatically. Crossing the outer boundary of the Kuiper Belt gives you one legitimate definition of leaving the planetary region of the solar system behind. Beyond the Kuiper Belt lies the scattered disk, a second population of icy objects thrown into highly elliptical orbits by gravitational interactions with Neptune. These objects range much farther from the Sun than the classic Kuiper Belt population, with some reaching 100 billion miles at their most distant points. The scattered disk has no clean outer edge. It dissolves gradually into the surrounding space, which is part of what makes defining the solar system so frustrating. Nature does not post signs at its boundaries. The next major boundary, and arguably the most physically meaningful one, is the heliopause. To understand it, you first need to understand the heliosphere. The Sun constantly emits a stream of charged particles, electrons and protons, moving outward at speeds of hundreds of miles per second. This stream is called the solar wind, and it fills an enormous bubble of space surrounding our star. The heliosphere is that bubble. Inside it, the Sun's wind dominates the particle environment. The pressure of solar wind holds back the interstellar medium, the thin gas and dust that fills the space between stars. But solar wind loses strength with distance. As it expands outward into an ever larger volume of space, its pressure drops. Eventually, at a distance of roughly 11 billion miles from the Sun, the solar wind slows to a stop, where its pressure finally balances the inward pressure of interstellar space. This boundary is the heliopause, and it represents one of the most scientifically compelling definitions of where the solar system ends. Cross the heliopause, and you have entered interstellar space. The Sun's direct physical influence, expressed through charged particles rather than gravity, no longer reaches you. Both Voyager probes have crossed this boundary. The data they returned confirmed that the particle environment changes dramatically on either side of it. But the heliopause is not the gravity boundary. The Sun's gravitational pull extends far beyond where its wind dies out. Gravity follows an inverse square law, weakening with distance but never reaching zero. The practical limit of the Sun's gravitational dominance lies in the Oort cloud, a roughly spherical shell of frozen objects extending from perhaps 2,000 times Earth's orbital distance to as far as 100,000 times that distance. Expressed in miles, the outer Oort cloud sits somewhere around 9 trillion miles from the Sun. These objects orbit so slowly and so far out that they complete a single circuit around the Sun only once every million years or more. Some of them have never been disturbed since the solar system formed 4.6 billion years ago. The Oort cloud has never been directly observed. Its existence is inferred from the behaviour of long-period comets. which arrive from the distant outer solar system on trajectories that could only originate from a vast reservoir of icy bodies. Occasional gravitational nudges from passing stars or giant molecular clouds dislodge these objects from their ancient orbits and send them falling inward toward the Sun, where they develop tails and become visible from Earth. The Oort cloud is the solar system's deep storage, the outermost structure still gravitationally bound to our star. This distinction between gravitational boundaries and particle boundaries matters enormously for the question of travel time. The heliopause sits at approximately 11 billion miles. The outer Oort cloud sits at roughly 9 trillion miles. That is a factor of more than 800 in distance. A journey to one takes decades. A journey to the other takes geological timescales under current propulsion. When someone asks how long it takes to reach the edge of the solar system, whether they know it or not, they're choosing between answers that differ by centuries. 3 candidate endpoints will anchor the rest of this examination. The first is the heliopause, the bubble edge where interstellar space technically begins, located around 11 billion miles out. It is the destination Voyager probes reached after 3.5 decades of travel. It represents the practical outer boundary of direct solar influence, and the point where you can genuinely say you have left the Sun's immediate environment behind. The second candidate is the Kuiper belt, specifically its outer edge, located at roughly 5 billion miles. It is closer, better mapped, and contains objects that might eventually become destinations in their own right. The third candidate is the Oort cloud, beginning at a few hundred billion miles and extending outward to nearly a light year from the Sun. It is the gravitational edge, the symbolic outermost limit, the answer you reach when you refuse to accept any boundary that the Sun's gravity does not enforce. Each boundary represents a different philosophy of what the edge means. The Kuiper belt edge is a structural boundary where the population of planetary debris finally runs out. The heliopause is a physical boundary where one medium transitions into another. The Oort cloud is a gravitational boundary where the Sun's dominion ends and the void between stars begins. A journey to any one of these locations would answer the original question, but the answers diverge so completely that comparing them feels like comparing different categories of human achievement entirely. The rest of this examination will hold all 3 in view simultaneously, measuring the challenge of reaching each against the capabilities of the technology humans have actually built, the biology humans actually inhabit, and the physics that governs any object moving through space. The definition you choose is not merely academic. It determines whether the journey in question is difficult, nearly impossible, or so far beyond current capability that calling it a journey at all requires a generous definition of the word. Numbers of the scale involved in solar system distances have a way of sliding past human comprehension without leaving a mark. 1 billion miles sounds large. So does 1 trillion. The difference between them sounds like a difference of degree when it is actually a difference of kind, and that confusion underlies almost every intuition failure people experience when thinking about space travel. Before examining how long a journey to the edge might take, it is worth building the scale from the ground up, using comparisons that the human mind can actually grip. Start with the Earth and Sun. The average distance between them is approximately 93 million miles, a unit astronomers have formalized as 1 astronomical unit, or a U. Light, travelling at 186,000 miles per second, covers this distance in about 8 minutes. When you look at the Sun, you're seeing it as it existed 8 minutes ago. The image is slightly out of date before it reaches your eyes. Now walk outward through the planets using this unit. Mars orbits at roughly 1.5 astronomical units. Jupiter, the largest planet, orbits at about 5.2 astronomical units. Saturn, with its rings, sits at 9.5 astronomical units. Uranus reaches 19 astronomical units. Neptune, the outermost recognized planet, orbits at approximately 30 astronomical units, or about 2.8 billion miles. Light takes roughly 4 hours to travel from the Sun to Neptune. A radio signal sent from Earth to a probe at Neptune arrives hours after it was transmitted. The planet that most people consider the outer edge of the solar system sits 30 times farther from the Sun than Earth does. This already stretches intuition, but it represents only the beginning of the structure. The outer edge of the Kuiper belt sits at approximately 50 astronomical units, double Neptune's distance from the Sun, and you have barely cleared the region of icy debris that extends beyond it. Light takes about 7 hours to reach the Kuiper belt's outer edge. The journey to what many people consider the planetary fringe of our system would take a signal from Earth the better part of a working day to complete. Here is where the scale begins to depart from anything familiar. The heliopause, where solar wind finally surrenders to interstellar pressure, sits at roughly 120 astronomical units from the Sun, not 30, not 50, 4 times Neptune's distance, 12 times Earth's distance from the Sun. Light takes approximately 17 hours to cross from the Sun to the heliopause. When Voyager 1 finally crossed this boundary in 2012, it had been travelling for 35 years. It was moving at about 38,000 miles per hour. At that speed, the drive from New York to Los Angeles would take less than 6 minutes. By human standards, Voyager 1 is extraordinarily fast. By solar system standards, it spent nearly 4 decades reaching what amounts to the first physically meaningful boundary. Now consider the Oort cloud, and here the numbers stop behaving like numbers at all. The inner edge of the Oort cloud begins at roughly 2,000 astronomical units. The outer edge extends to somewhere between 50,000 and 100,000 astronomical units. Take a moment with the outer figure, 100,000 times Earth's distance from the Sun. At that distance, light takes over a year to arrive from our star. The Sun from the outer Oort cloud would appear as an exceptionally bright star rather than a blazing disk. It would still outshine everything else in the sky, but it would cast no warmth on any surface it illuminated. The solar system's gravitational envelope encompasses a sphere almost 2 light-years across, reaching nearly halfway to the nearest stellar neighbour. A useful comparison anchors this in physical reality. Imagine shrinking the entire solar system so that Earth's orbit around the Sun becomes 1 inch across. At this scale, Neptune's orbit spans roughly 30 inches, less than a yard. The outer Kuiper belt sits at about 50 inches. The heliopause reaches approximately 120 inches, or 10 feet. Still manageable, the kind of scale a room can contain. But the inner Oort cloud at this scaling sits about 167 feet away. The outer Oort cloud extends more than a mile from your original starting point. The planets and the heliopause fit inside a large room. The true gravitational boundary of the solar system requires a mile of open space to represent. This scaling exercise reveals something counterintuitive about how our mental picture of the solar system fails us. Popular diagrams of the solar system show 8 planets arranged at seemingly reasonable intervals, with Neptune marking the far boundary. These diagrams compress the outer solar system enormously to fit on a page, and viewers absorb this compressed geometry as truth. The actual solar system devotes the overwhelming majority of its volume to regions far beyond Neptune, regions with no planets, no probes, and no direct human observation. What we think of as the solar system, the familiar disk of planets, is a tiny warm kernel inside an enormous cold sphere of frozen debris and gravitational influence. The distinction matters practically because distance compounds with speed in ways that punish small velocity differences severely at extreme range. Consider 2 spacecraft departing Earth simultaneously, one travelling at 38,000 miles per hour and another travelling at 40,000 miles per hour. After 1 year, the faster spacecraft leads by roughly 17.5 million miles. At the heliopause, 120 astronomical units out, the faster craft arrives approximately 2 years sooner. The difference is meaningful, but not transformative. Apply those same two speeds across the journey to the outer Oort cloud at 100,000 astronomical units, and the faster spacecraft arrives decades before its slightly slower counterpart. Small velocity advantages that seem trivial over planetary distances become staggering over the distances required to reach the solar system's true edge. A spacecraft travelling twice as fast does not take half as long to reach Neptune, and then continue proportionally shortening every subsequent journey. It takes half as long to reach every destination, and the destinations in the outer solar system are so vastly more distant than the planets that the time savings dwarf anything measurable in the planetary realm. This is why the question of travel time cannot be separated from the question of which edge you mean to reach. The heliopause is distant by any planetary measure but comprehensible in human terms, decades of travel with existing technology. The inner Oort cloud, beginning 2,000 astronomical units out, sits more than 16 times farther. The outer Oort cloud extends nearly 1,000 times beyond the heliopause. Each layer multiplies the journey time by factors that eventually push the numbers past centuries and into millennia. And throughout all of this, the human body continues aging at its ordinary pace, indifferent to the grandeur of the distances involved. The solar system's size would be merely an impressive fact if travellers had unlimited time to cross it. They do not. That constraint is what transforms scale from an astronomical curiosity into the central problem of any serious conversation about reaching the edge. Against those distances, the natural next question is how fast we actually move through space. Not theoretically, not with propulsion systems yet to be built, but how fast human beings have actually travelled aboard real vehicles during missions that launched, flew, and returned. The answer establishes the baseline against which everything else must be measured, and it is both more impressive than most people realise and more inadequate than the solar system's scale demands. The fastest human beings in history were the crew of Apollo 10, the 1969 mission that served as the full dress rehearsal for the lunar landing. During their return to Earth, the capsule reached a speed of approximately 24,791 miles per hour as it fell back into Earth's gravitational well. This record has stood for over 5 decades. No human crew has travelled faster before or since. 24,000 miles per hour sounds extraordinary by any surface standard. A commercial airliner cruises at roughly 575 miles per hour. A rifle bullet travels around 1,700 miles per hour. The Apollo 10 crew moved more than 14 times faster than a rifle bullet. They covered roughly 7 miles every second. But the context of that speed matters enormously. The Apollo 10 crew achieved that velocity not through brute propulsion, but through gravitational acceleration. As their capsule fell toward Earth from the Moon, Earth's gravity pulled them faster and faster, just as a ball rolling down a steep hill accelerates without any engine pushing it. The actual propulsion required to place them on that return trajectory was relatively modest. The peak velocity was a gift from gravity, not a sustained capability of their spacecraft. This distinction separates peak mission speed from what engineers call cruise speed, the velocity a spacecraft maintains while travelling through open space far from any massive body's gravitational influence. The Saturn V rocket, the most powerful launch vehicle ever successfully operated by humans, burned through its massive fuel reserves to place the Apollo capsule on a trajectory toward the Moon. By the time the spacecraft reached deep space, it was coasting. Drifting, really, on the momentum imparted during those first minutes of powered flight, then adjusting trajectory with small engine burns. A spacecraft coasting without thrust in deep space follows whatever velocity it earned during acceleration. It does not continue speeding up. It maintains its cruise speed until something changes it. The cruise speed of the Apollo missions to the Moon was far lower than the peak re-entry velocity. During the transit between Earth and Moon, the spacecraft moved at speeds averaging somewhere around 3,000 to 5,000 miles per hour, depending on the phase of the journey, slowing as it climbed away from Earth's gravity, and then accelerating again as the Moon's weaker gravity pulled it in. These are the speeds that matter for thinking about deep space travel, not the dramatic peak velocities created by falling toward a planet. Robotic probes have achieved dramatically higher speeds than any crewed spacecraft, and the comparison reveals how much the requirement to carry humans constrains velocity. The Parker Solar Probe, which has no crew and carries only scientific instruments, has reached speeds exceeding 430,000 miles per hour during its closest approaches to the Sun. This is not a coincidence. The probe uses repeated Venus gravity assists and the enormous gravitational acceleration of approaching the Sun to reach these velocities, but the underlying point stands. Without a crew, mission designers can optimize entirely for speed. Without a crew, there is no need for life support systems, pressurized compartments, radiation shielding adequate for biological tissue, food, water, thermal regulation for human comfort, or emergency return capability. A crewed spacecraft carries all of these systems, and every system adds mass. Mass is the central problem. The energy required to accelerate any object to a given velocity scales directly with that object's mass. Double the mass, and you double the energy required to reach the same speed. A crewed spacecraft might mass 50,000 kilograms or more when fully equipped for a deep space mission. The Parker Solar Probe has a mass of roughly 685 kilograms. The probe is lighter by a factor of 70 or more, and that difference translates directly into achievable velocity for a given amount of propulsion energy. The laws of physics do not offer exceptions for ambition. Chemical propulsion, which has powered every crewed spacecraft in human history, operates through the controlled combustion of propellant. The fundamental performance limit of a chemical rocket is determined by the energy density of its fuel and the efficiency with which that energy converts to thrust. The Saturn V's engines burned liquid hydrogen, liquid oxygen, among the highest performing chemical propellants available. The exhaust velocity of those engines reached approximately 14,400 miles per hour. No chemical engine can throw exhaust faster than the energy content of its fuel permits. This physical ceiling on exhaust velocity creates a hard ceiling on achievable spacecraft velocity, regardless of how much fuel you carry. Adding more fuel adds mass to be accelerated, triggering the diminishing returns that rocket engineers call the tyranny of the rocket equation. The best chemical rockets ever built can accelerate a spacecraft to roughly 25,000 to 35,000 miles per hour above Earth's orbital velocity, depending on how aggressively the fuel is consumed. Voyager 1, boosted by gravity assists from Jupiter and Saturn, eventually reached a cruise speed of approximately 38,600 miles per hour, making it the fastest human-made object in sustained deep space travel. This record reflects decades of accumulated small accelerations from carefully chosen gravitational slingshots around massive planets, not raw propulsive power. And Voyager 1 carries no crew. For a crewed spacecraft using the best chemical propulsion available, realistic deep space cruise speeds fall somewhere in the range of 25,000 to 40,000 miles per hour, depending on gravity assists and mission design. These velocities are genuine achievements of engineering and human ingenuity. They are also, when measured against the distances to the solar system's outer boundaries, almost heartbreakingly slow. At 40,000 miles per hour, A crewed spacecraft would cover roughly 350 million miles per year. Earth's distance from the Sun is 93 million miles. Neptune's distance is approximately 2.8 billion miles. The heliopause sits at roughly 11 billion miles. The inner Oort cloud begins at over 185 billion miles. The outer Oort cloud extends past 9 trillion miles. Running those numbers against a cruise speed of 40,000 miles per hour produces journey durations measured in decades to reach the heliopause and thousands of years to reach the Oort cloud. This is the honest baseline. Human beings have travelled in space for over 6 decades. The fastest we have ever moved is just under 25,000 miles per hour, achieved briefly during gravitational re-entry. Our most capable crewed spacecraft could sustain perhaps 40,000 miles per hour in deep space with favourable conditions and gravity assists. Our fastest robotic probes outrun our fastest crewed vehicles by an order of magnitude, and even those probes took 35 years to reach the first meaningful boundary of the outer solar system. Before discussing what might be possible with different propulsion systems, this is where humanity actually stands. Every improvement, every ambitious concept, every calculation about future journey times must start from this foundation. Take that baseline and apply it to a real human mission, not a thought experiment, not a probe with instruments and no heartbeat, but an actual crewed spacecraft carrying people who need air and food and water and warmth and medical care across years of empty space. The engineering picture that emerges is sobering in ways that raw speed numbers alone do not capture. The first constraint is propulsion, and it is as fundamental as physics allows. Chemical rockets remain the only propulsion technology ever used to fly human beings in space. Every crewed mission in history, from Yuri Gagarin's single orbit to the International Space Station crew rotations to the Apollo lunar landings, has relied on the controlled combustion of propellant. The specific impulse of the best chemical engines, a measure of how efficiently they convert propellant mass into thrust, tops out around 450 seconds for liquid hydrogen and liquid oxygen systems. This ceiling is not an engineering failure waiting to be corrected. It reflects the actual energy content of chemical bonds. You cannot extract more energy from a combustion reaction than the chemistry contains, and the chemistry has been optimized extensively over 7 decades of rocket development. The rocket equation punishes deep space missions with a particular cruelty. The propellant required to reach a given velocity grows exponentially with the velocity you want to achieve. Doubling your target speed requires far more than doubling your fuel. For a crewed spacecraft targeting deep space velocities, the propellant mass can easily exceed the payload mass by a factor of 10 or more, and that ratio worsens as mission duration and payload mass increase. Longer missions require more life support consumables. More consumables add mass. More mass requires more propellant. More propellant adds mass. The spiral tightens with each constraint you add. Now consider what a human crew actually needs. A mission to the outer solar system would require a pressurized habitat large enough to prevent the psychological deterioration that accompanies extreme confinement, structural shielding adequate to block galactic cosmic rays and solar energetic particles from penetrating biological tissue, thermal control systems to maintain temperatures compatible with human life through years of deep space cold, power generation sufficient to run all these systems continuously, and redundant versions of every critical component, because a single point of failure that kills one person on a 6-month trip to the moon kills everyone on a 6-year trip to Neptune. These requirements are not negotiable. Human physiology establishes them. Radiation shielding alone is an enormous engineering burden. In low Earth orbit, Earth's magnetic field deflects most high-energy particles. Beyond that protection, cosmic radiation exposure accumulates continuously. Water is among the better passive shielding materials, and missions of several years' duration would require either substantial water walls surrounding crew quarters or pharmaceutical and biological countermeasures whose effectiveness over such timescales remains unproven. Passive shielding adequate to meaningfully reduce cosmic ray exposure might add tens of thousands of kilograms to the spacecraft. Every kilogram added to the spacecraft reduces the velocity achievable with a given propulsion system, or alternatively requires proportionally more propellant to maintain the same velocity. A realistically designed crewed mission to the outer solar system using current technology might mass somewhere between 100,000 and 500,000 kilograms at departure, depending on destination, mission duration, and the level of redundancy built in. The Saturn V, the most capable launch vehicle humans have ever operated, could deliver roughly 130,000 kilograms to low Earth orbit. A single launch would not suffice. Multiple launches would be required to assemble such a mission, adding operational complexity and cost. The mass requirements alone make the economics daunting before the propulsion calculations even begin. Orbital mechanics offer partial relief. Gravity assists, the technique of swinging a spacecraft past massive planets to steal a fraction of their orbital momentum, can add meaningful velocity without consuming additional propellant. Voyager 1's journey to the outer solar system exploited a rare planetary alignment to chain together gravitational slingshots around Jupiter and Saturn, dramatically increasing its final cruise speed. A crewed mission could employ similar techniques, but the geometry of available gravity assists depends on planetary positions that recur only occasionally. A mission designed around optimal gravity assists would have narrow launch windows years apart, and the trajectory constraints those windows impose might not align with the fastest possible route. Gravity assists help. They do not transform the fundamental limitation. Working through the numbers honestly, a crewed spacecraft using chemical propulsion and gravity assist opportunities could realistically cruise at somewhere between 30,000 and 60,000 miles per hour, depending on mission design and timing. At 50,000 miles per hour, reaching Neptune requires roughly 6 to 7 years. This is not an inherently impossible duration for a crewed mission. International Space Station crew members have accumulated stays approaching 1 year. But the ISS benefits from continuous resupply missions, immediate evacuation options in case of emergency, and the psychological reassurance of seeing Earth through the windows. A crew beyond Jupiter has none of these lifelines. They carry everything they will need for the entire journey, because nothing can reach them and no rescue is possible. The mass of consumables for a crew of even 4 people over a 6-year mission is substantial. Food production in space using closed-loop agricultural systems remains experimental and has never been demonstrated at mission scale. Carrying all food as packaged supplies would add enormous mass. Water can be recycled with high efficiency using current ISS technology, but high efficiency is not perfect efficiency, and losses accumulate over years. Atmospheric regeneration, waste processing, and medical supplies further compound the mass budget. The mission that looked barely feasible on paper begins looking genuinely formidable when every line item is filled in honestly. Beyond Neptune, the timescales escape the range of any crewed mission that existing technology could sustain. Reaching the heliopause at roughly 11 billion miles from the Sun, where Voyager 1 crossed after 35 years of flight, would take a crewed spacecraft travelling at 50,000 miles per hour, approximately 25 years. 25 years is not a mission. It is a significant portion of an adult human life. The crew would depart in middle age and arrive, if the spacecraft and its systems held together, as elderly people, if they arrived at all. The critical distinction here is between an engineering limit and a physics limit. Nothing in the laws of physics prevents a chemical rocket from reaching these velocities. The propulsion works, the trajectories exist. The limitation is entirely practical, material and human. The spacecraft becomes too massive to accelerate adequately. The mission duration exceeds what current life support technology can reliably sustain. The radiation exposure over decades exceeds acceptable biological limits. These are problems of engineering and biology, not violations of physical law. That distinction matters enormously for thinking about what better technology could change and what it cannot. Physics sets the ceiling. Engineering so far keeps us nowhere near it. If you want to understand what crossing the solar system actually costs in years, the Voyager probes are the most honest teachers available. Not theoretical mission designs sketched on paper, not optimistic projections built around propulsion technologies that do not yet exist. 2 real spacecraft launched with real rockets, travelling through real space for a duration no crewed mission has ever approached. They are imperfect benchmarks for human travel, as this section will carefully note. But they are the only benchmarks we have, and what they reveal about time and distance is worth examining in detail. Voyager 1 launched in September 1977. Voyager 2 followed 16 days later on a different trajectory. Both were designed to exploit a rare geometric alignment of the outer planets, a configuration that occurs roughly once every 175 years and that engineers at the Jet Propulsion Laboratory recognized as an unrepeatable opportunity. The planetary positions of the late 1970s allowed a single spacecraft to visit multiple outer planets in sequence, using the gravity of each to sling itself toward the next. Without this alignment, the energy cost of reaching each destination individually would have been far higher. With it, the mission became something extraordinary. The mechanics of a gravity assist deserve a moment of attention because they are easy to misunderstand. When Voyager 1 swung past Jupiter in March 1979, roughly 18 months after launch, it did not simply get deflected. It stole orbital momentum from the planet. Jupiter, orbiting the Sun at roughly 29,000 miles per hour, is an enormous reservoir of kinetic energy. A spacecraft passing on the correct trajectory can emerge from the encounter moving faster than it arrived, while Jupiter loses an immeasurably tiny fraction of its own orbital velocity. The exchange is real and measurable. The spacecraft gains speed without burning additional propellant. From a purely energetic standpoint, it is the closest thing to a free lunch that orbital mechanics offers. Voyager 1's Jupiter flyby accelerated it significantly. Its Saturn encounter in November 1980 added more. By the time it left the Saturn system, Voyager 1 was travelling at approximately 38,000 miles per hour relative to the Sun. This remains among the highest velocities ever achieved by a human-made object. It also represents a velocity that was only possible because the planets were positioned exactly where they needed to be at exactly the right time, and because the spacecraft had no crew, no life support systems, no radiation shielding for human tissue, and no requirement to ever decelerate. Voyager 1 is still accelerating slightly from the Sun's gravitational influence in reverse, what scientists call hyperbolic escape velocity, meaning it will never fall back. Voyager 2 followed a longer route, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. 12 years from launch to Neptune. The distance at Neptune encounter was roughly 2.7 billion miles from the Sun. 12 years for 2.7 billion miles, even with gravity assist stacking velocity at each planet, gives a sense of the scale involved. Neptune is not the edge of the solar system by any serious definition, but it is the most distant planet, and reaching it consumed more than a decade of uncrewed flight. After Neptune, Both spacecraft entered a long coasting phase with no further planets to assist them. The Sun's gravity continued to slow them, though not enough to prevent escape. Voyager 1 crossed the termination shock, where the solar wind slows abruptly as it encounters interstellar pressure, around 2004, roughly 27 years after launch. It crossed the heliopause itself in 2012, 35 years after departing Earth. At that moment, instruments aboard confirmed that the plasma environment had shifted character, that the bubble of the Sun's direct influence had been left behind. Voyager 1 had travelled approximately 11 billion miles from the Sun, 35 years to cover 11 billion miles. Voyager 2 crossed the heliopause in 2018, 41 years after launch, at a somewhat different distance in a different direction. The heliopause is not a perfect sphere. The Sun moves through the interstellar medium, creating an asymmetric bubble that extends farther in some directions than others. The two crossings confirmed that the boundary is real, measurable and passable, but also that reaching it demands timescales that dwarf any crewed mission ever attempted. What Voyager actually reached, and what it did not, matters for calibrating expectations. Both probes are now in interstellar space by the definition that they have crossed the heliopause. They have not reached the Oort cloud, the vast reservoir of cometary bodies that represents the solar system's outermost gravitational dominion. The Oort cloud begins perhaps 1,000 times farther from the Sun than the heliopause, and extends perhaps halfway to the nearest star. At Voyager 1's current velocity, reaching the inner Oort cloud would require roughly 300 years. Traversing its full extent would require thousands of years more. The Voyager probes, our fastest long-duration travellers, will not complete a crossing of our own solar system within any time frame relevant to human civilization as it currently exists. The lessons these missions offer for human travel must be drawn carefully. Voyager achieved what it achieved because it carried no crew. The spacecraft massed roughly 825 kilograms each at launch. They required no food, no water, no pressurized habitat, no radiation shielding for biological tissue. When components failed over the decades, and they did, mission controllers adapted by reprogramming the spacecraft remotely, accepting degraded functionality rather than making repairs. A crewed spacecraft cannot accept degraded life support functionality. It cannot wait months for a software patch when the air recycler malfunctions. The gravity assists that gave Voyager 1 its velocity were also a product of timing that cannot simply be reproduced on demand. The planetary alignment of 1977 recurs on a 175-year cycle. A future mission could use Jupiter and Saturn for gravity assists outside this window, but stringing together 4 or 5 planetary flybys in sequence requires the planets to cooperate geometrically, and they do not always cooperate on schedules that match mission requirements. There is also the question of propulsion at launch. Voyager was lofted on a Titan Centaur rocket, a capable vehicle for its era, and even with gravity assists, its cruise speed is far below what would be needed to make a crewed outer solar system mission practical within a human working lifetime. A crewed spacecraft with 50 times the mass would not simply reach 50 times slower. The relationship is worse than linear. The mass penalty cascades through the mission design in ways examined in the previous section. None of this diminishes what Voyager accomplished. These machines returned data from the outer planets that transformed planetary science, crossed into true interstellar space while still transmitting coherent information, and demonstrated that carefully engineered systems can function across decades of deep space operation. They answered the question of whether crossing the heliosphere is physically possible. The answer is yes. What they cannot answer is whether humans can do it quickly enough to matter for the people who make the journey. Voyager 1 took 35 years to reach a boundary that represents only the inner threshold of the solar system's outermost regions. That is the honest benchmark. Everything more ambitious than that requires technology Voyager never had, and humans have yet to build. Voyager 1 crossed the heliopause in 2012 and never looked back. But what exactly did it cross? And why do scientists and mission planners treat this particular boundary as the most meaningful operational edge of the solar system, rather than some arbitrary line drawn through empty space? The heliopause is the surface where the sun's influence over its immediate environment effectively ends. To understand it requires understanding the solar wind, the continuous stream of charged particles, mostly protons and electrons, that the sun blasts outward in all directions at speeds between 1 and 3 million miles per hour. This outflow is not gentle. It is energetic enough to carve a vast cavity in the surrounding interstellar medium, a bubble of solar-dominated space called the heliosphere. Inside this bubble, the particles, magnetic fields, and radiation environment are primarily governed by our star. Outside it, they are governed by the broader galaxy. The heliopause is the outer membrane of that bubble, the surface where solar wind pressure finally balances the pressure of interstellar plasma flowing in the opposite direction. It is not a sharp wall, but a transition region, a zone where the character of the plasma environment shifts from something solar to something interstellar. Voyager's instruments detected this shift in two ways. The density of low-energy particles originating from the sun dropped sharply, and the density of cosmic rays originating from outside the solar system increased sharply. The crossings confirmed the boundary is real, physically meaningful, and directionally asymmetric depending on how the sun happens to be moving through the local interstellar medium at any given moment. Many scientists and space agencies treat the heliopause as the most defensible operational definition of where the solar system ends, not because nothing interesting lies beyond it, but because it represents the point at which the sun's direct physical dominion over the local environment ceases. Beyond the heliopause, you're swimming in interstellar space in every physically meaningful sense. The sun becomes simply one star among others, distinguished only by its gravitational pull, which continues for much farther, but does not shape the immediate particle environment you inhabit. So how long would it take humans to get there? Voyager 1 required 35 years travelling at roughly 38,000 miles per hour, a velocity achievable only through a chain of planetary gravity assists that cannot simply be replicated on demand. A crewed spacecraft mission designed today, using the best human-rated propulsion systems currently available or near-term feasible, would look considerably different. Consider several scenarios honestly. A spacecraft using advanced chemical propulsion combined with a Jupiter gravity assist, roughly the best capability available without exotic technology, might sustain average speeds of 50,000 to 60,000 miles per hour on an optimized trajectory. At 55,000 miles per hour, reaching the heliopause at a distance of roughly 120 astronomical units from the Sun, equivalent to about 11 billion miles, would take approximately 23 to 25 years. Better than Voyager's timeline, but still a mission that would consume the better part of a scientific career and demand that crew members commit their working lives to a single voyage with no clear means of rescue if something went wrong at the halfway point. Push propulsion technology harder. Nuclear thermal propulsion, a technology developed and tested during the 1960s and 1970s, but never flown operationally, could potentially double or triple the velocities achievable with chemical rockets. At 150,000 miles per hour, the heliopause becomes reachable in roughly 8 to 10 years. That begins to enter the range of what a properly selected crew could endure, though it still represents a mission longer than any crewed spaceflight ever attempted by a factor of approximately 20. The longest anyone has spent continuously in space is roughly 14 months. A decade-long mission to the heliopause would require life support systems, psychological frameworks, and medical capabilities that do not currently exist in tested form. More advanced concepts push the timeline down further. a spacecraft using nuclear pulse propulsion similar in concept to Project Orion, firing nuclear detonations to drive a pusher plate, could potentially reach 3 to 4% of light speed, roughly 20 million miles per hour. At those velocities, the heliopause becomes a journey measured in weeks rather than years. But this remains firmly in the territory of technology that has never been tested at scale, and faces political and treaty obstacles beyond purely engineering ones, even granting the optimistic scenario in which some advanced propulsion system delivers a human crew to the heliopause within a decade. Crossing the boundary would not resolve the broader question of what it means to reach the solar system's edge. The heliopause marks the end of the Sun's particle dominion, but it leaves the Sun's gravitational dominion almost entirely intact. The Oort cloud, the vast spherical reservoir of cometary objects gravitationally bound to our star, begins somewhere around 1,000 to 2,000 astronomical units and extends perhaps 100,000 astronomical units outward. A ship crossing the heliopause at 120 astronomical units has travelled roughly 1/10% of the distance to the Oort cloud's outer boundary. Gravitationally speaking, it has barely left the driveway. This tension between different definitions of the edge is not merely academic. It matters enormously for how any mission to the heliopause would be framed publicly and scientifically. Crossing the heliopause would be a genuine achievement, a first for crewed spaceflight, the moment humans physically entered the interstellar medium. It would not be the same as escaping the solar system in the gravitational sense that mathematicians and orbital mechanics engineers use. Beyond the heliopause, the radiation environment changes in ways that matter deeply for human biology. Inside the heliosphere, the solar wind and the Sun's magnetic field provide partial shielding against galactic cosmic rays. The high-energy particles streaming in from supernovae and other energetic events throughout the galaxy. The heliosphere is not perfect shielding by any means, but it does attenuate the cosmic ray flux meaningfully. Beyond the heliopause, that attenuation disappears. Galactic cosmic ray exposure increases substantially, and these particles are among the most dangerous forms of radiation known, because their high energies allow them to penetrate almost any practical physical shielding. The Voyager spacecraft confirmed this. When Voyager 1 crossed the heliopause, its cosmic ray instruments registered a clear increase in galactic cosmic ray intensity. For an uncrewed probe, this is a data point. For a crewed spacecraft, it is a serious health concern. Extended exposure to galactic cosmic rays damages DNA, increases cancer risk, and is increasingly suspected of contributing to neurological degradation. Any crewed mission beyond the heliopause would need radiation protection strategies that current technology cannot fully provide. Whether a human mission to the heliopause is plausible on a multi-decade timescale depends almost entirely on which propulsion technology is assumed. With nuclear thermal propulsion brought to operational status and life support technology extended to decade-long missions, a crew could potentially reach the heliopause within a working career. With advanced nuclear pulse propulsion, the travel time drops to something more survivable. With only chemical rockets and current life support technology, the mission remains beyond practical reach for living crews, as Voyager's 35-year timeline makes brutally clear. The heliopause is the most honest first candidate for a meaningful edge. It is physically real, scientifically definable, and confirmed by 2 spacecraft that actually crossed it. Getting humans there is not theoretically impossible. It is an engineering problem of staggering difficulty that requires propulsion and life support advances beyond anything yet demonstrated, in exchange for the first moment in history when human beings would float in interstellar space and look back at the Sun as simply one star among many. The heliopause sits at roughly 120 astronomical units from the Sun and commands serious scientific respect as a boundary. but for many people first encountering the scale of the solar system, an earlier region captures the imagination more viscerally. The Kuiper belt begins around 30 astronomical units, extends outward to perhaps 50, and contains some of the most famous objects in the solar system beyond the 8 classical planets. Pluto lives here. So does Eris, Makemake, Haumea, and thousands of smaller bodies. If you're trying to explain to someone where the solar system's edge might be found, the Kuiper belt feels like an intuitive answer. It is the place where the well-ordered planetary zone gives way to something wilder and more crowded with debris. The problem with this intuition is that the Kuiper belt is not a neat border. It does not present a clear membrane the way the heliopause does. It is a broad, diffuse region, a disk of icy objects orbiting the Sun in the same general plane as the planets, but spread across a substantial range of distances and inclinations. Entering the Kuiper belt is not like crossing a line. It is more like walking from a manicured garden into a meadow. The transition is gradual, the density of material increases, and the character of what you encounter changes, but there is no moment of arrival. Any mission description claiming to reach the Kuiper belt rather than a specific object within it is really describing a zone transit rather than a destination. This distinction matters enormously for mission planning. Pluto, visited by the New Horizons spacecraft in 2015, orbits at roughly 39 astronomical units on average, though its elliptical orbit carries it between about 30 and 49 astronomical units over its 248-year period. Eris, the dwarf planet whose discovery directly triggered the reclassification of Pluto, orbits at a highly elliptical path that currently places it near 96 astronomical units from the Sun, nearly as far as the heliopause itself. Both objects are described as Kuiper belt residents in casual usage, yet they differ in distance by a factor of nearly 3. Choosing Pluto as your destination and choosing Eris as your destination are completely different missions, separated by decades of additional travel time. The New Horizons probe reached Pluto in approximately 9.5 years after its launch in January 2006, making it the fastest spacecraft ever launched at the time of its departure. It travelled at speeds approaching 36,000 miles per hour and required no extended cruise phase of slow propulsion building. Even so, 9.5 years represents a significant duration. For a crewed mission using comparable technology, reaching Pluto's distance would demand life support for a decade in deep space, and a crew willing to commit the entirety of that time to the outbound journey alone, with no resupply and no practical rescue option. The return trip would require either a very long wait for favourable orbital geometry, or a trajectory so indirect that the total mission duration stretches to 20 years or more. With advanced nuclear thermal propulsion capable of tripling or quadrupling current spacecraft velocities, the picture improves meaningfully. At roughly 150,000 miles per hour, a spacecraft could reach Pluto's average orbital distance in approximately 2 to 3 years. That approaches the edge of what crewed deep space architecture might realistically support, with significant investment in life support and radiation shielding. It is still more than twice the longest crewed spaceflight ever completed, but it is no longer an exercise in pure speculation. It is a formidable engineering challenge with a plausible path forward, given sustained commitment. Beyond the classical Kuiper belt lies the scattered disk, and here the picture becomes considerably messier. The scattered disk is a dynamically perturbed population of icy bodies whose orbits have been stretched and tilted by gravitational interactions, primarily with Neptune during the early solar system's chaotic period of orbital migration. These objects do not sit quietly in a neat belt. Their orbits carry them on highly elliptical paths that swing from the inner Kuiper belt region out to distances of several hundred astronomical units or more. Sedna, one of the most distant known solar system objects with a confirmed orbit, swings between approximately 76 and 937 astronomical units. Its orbital period is roughly 11,000 years. It is gravitationally bound to our Sun, orbiting it reliably, but at distances that dwarf anything in the classical planetary zone. The scattered disk blurs the boundary problem considerably. If you define the edge of the solar system as the outer limit of objects orbiting the Sun in the disk plane, the scattered disk pushes that boundary to several hundred astronomical units, well beyond the heliopause. But the heliopause sits at 120 astronomical units, meaning these scattered disk objects orbit partly inside and partly outside the boundary where the Sun's particle dominion ends. Gravity and particle environment disagree about where the solar system stops. The same body can spend part of its orbit in nominally interstellar space while remaining gravitationally bound to the Sun for thousands of years. For travel time estimates, the scattered disk introduces a practical complication. If you want to visit a scattered disk object near its closest approach to the Sun, the journey might be comparable to visiting the classical Kuiper belt, perhaps a few hundred astronomical units at most. But if you want to intercept a scattered disk object near its aphelion, the distant end of its orbit, you're talking about a journey several times longer than reaching the heliopause. The same class of object presents wildly different mission durations depending on where it happens to sit in its orbit at the time you launch. What makes the Kuiper belt and scattered disk easier to imagine reaching than the truly distant edges is precisely their familiarity. We have sent a spacecraft to Pluto. We have names for specific objects. Pluto has moons, a heart-shaped plain of nitrogen ice, and a complicated atmosphere that fluctuates with the seasons. Eris has a companion moon named Dysnomia. These places feel like destinations because we have resolved them as worlds rather than points of light. The Oort cloud, which extends perhaps 100,000 astronomical units from the Sun, contains no named landmarks at all and has never been directly observed, only inferred from the trajectories of long-period comets falling inward past the planets. The psychological reality of exploration is that people need objects, not zones. A mission to the Kuiper belt is actually a mission to a specific body within it, and choosing which body determines whether you are planning a decade-long endeavour or something closer to a generation-spanning commitment. Pluto represents the more tractable end of that range. Eris represents something considerably harder. Scattered disk objects near their distant orbital limits represent something that current technology cannot address at all on human timescales. What the Kuiper belt and scattered disk ultimately reveal is that the solar system does not resolve neatly into an inside and an outside. It dissolves gradually through zones of decreasing order and increasing travel time, each zone blurring into the next, each definition of edge creating a different mission and a different time scale. The heliopause ends the Sun's particle dominion. The scattered disk stretches the gravitational inventory of the solar system to distances that demand entirely new ways of thinking about what reaching the edge could possibly mean. Beyond the scattered disk, beyond Sedna's extraordinary 11,000-year orbit, beyond every named object and every region with any direct observational support, lies a structure so enormous that calling it part of the solar system strains the ordinary meaning of the phrase. The Oort cloud is not a place anyone has ever seen. No spacecraft has visited it. No telescope has resolved individual objects within it. It exists in our understanding entirely as an inference, a theoretical construct demanded by the behaviour of comets, falling into the inner solar system on trajectories that can only be explained by a vast distant reservoir surrounding the Sun in every direction. The comets arrive from all inclinations, from above and below the ecliptic plane, from angles that a flat disk structure could never produce. Something spherical, something enormous must be sending them inward. That something is the Oort cloud. The numbers involved are not merely large. They belong to a different category of large than anything encountered in discussions of the planets, or even the heliopause. The inner Oort cloud, sometimes called the Hills cloud, begins somewhere around 2,000 astronomical units from the Sun and extends to perhaps 20,000. The outer Oort cloud stretches from there to perhaps 100,000 astronomical units, nearly halfway to the nearest star. The Sun sits at the centre of a shell of icy bodies, extending roughly 1/5 to 1/4 of the distance to Proxima Centauri. When astronomers speak of the gravitational reach of our Sun, when they describe the full domain over which solar gravity dominates, the Oort cloud is that domain. The solar system, defined by gravity rather than by planetary architecture or particle environment, is almost inconceivably larger than the region most people picture when they hear the term. To understand what these distances mean for travel, the calculations need only be performed once, before the results become almost philosophically uncomfortable. The Voyager probes, currently the most distant human-made objects and the only spacecraft to cross the heliopause, travel at roughly 35,000 miles per hour. At that speed, reaching the inner edge of the Oort cloud at 2,000 astronomical units would require approximately 1,200 years. Reaching the midpoint of the inner cloud at 10,000 astronomical units would require around 6,000 years. Reaching the outer boundary of the Oort cloud at 100,000 astronomical units would require roughly 58,000 years. For comparison, 58,000 years ago, anatomically modern humans had not yet left Africa in significant numbers. The entirety of recorded human history, all of agriculture and writing and civilization, fits inside a period less than 1/10 that long. No serious engineer considers Voyager-class propulsion adequate for a mission to the Oort cloud. Apply more optimistic propulsion technology, and the figures improve, though they remain staggering. Nuclear pulse propulsion of the Project Orion variety, achieving perhaps 4% of light speed under ideal conditions, would reach the inner Oort cloud in roughly 3 years. That sounds manageable until you account for the fact that the inner edge is only the beginning. Reaching the midpoint of the outer cloud at 50,000 astronomical units would still require around 160 years at 4% of light speed. A spacecraft travelling at a full 10% of light speed, representing propulsion technology well beyond anything currently built or tested, would reach that same midpoint in approximately 65 years, still longer than a human career, still beyond the reach of any mission crew that launched as adults expecting to complete the journey themselves. Even a spacecraft travelling at a hypothetical 20% of light speed, a velocity that would require propulsion systems representing a revolution beyond current capability, would require roughly 33 years to reach the outer edge of the Oort cloud. The outer Oort cloud, as a destination, exists outside the reach of a single human lifetime at any velocity that remains physically credible using known propulsion principles. The inner Oort cloud presents a more tractable, but still sobering picture. At 10% of light speed, a spacecraft reaches the inner boundary in approximately 3 years, that places specific objects within the inner cloud, should any ever be identified and targeted, within the range of a crude mission architecture. But the inner Oort cloud contains no known named objects, no resolved bodies, nothing with a defined position or confirmed composition. Its population is inferred but individually invisible. Mounting a crewed mission to the inner Oort cloud without a specific identified destination is not exploration. It is simply traversal of empty space at the edge of the Sun's gravitational reach. What the Oort cloud clarifies, more starkly than any other structure in the solar system, is the difference between the Sun's gravitational domain and anything a human civilization might reasonably visit. Gravity is patient and works at arbitrary distances, holding the Oort cloud loosely bound across scales measured in light years. human missions are not patient. They're constrained by lifetimes, by consumables, by the biological imperative that the people who depart are also the people who arrive. Gravity can maintain dominion over 100,000 astronomical units without effort. A human spacecraft cannot cross 100,000 astronomical units without a multi-generational commitment rivaling the duration of entire historical civilizations. There is something disorienting about this realization at the conceptual level. The Oort cloud is not beyond the solar system. It is the solar system, or the outermost part of it, the gravitational envelope that defines where the sun's influence ends and true interstellar space begins. When the Voyager probes crossed the heliopause and entered what NASA described as interstellar space, they had travelled roughly 120 astronomical units. The sun's gravitational reach extends nearly 1,000 times further. The Voyager probes are, by any gravitational definition, still very much inside the solar system. They will remain inside the solar system for tens of thousands of years, unless something perturbs their trajectories. The Oort cloud also illustrates something important about the relationship between distance and isolation. Objects in the outer Oort cloud receive so little sunlight that a spacecraft approaching them would find no usable solar energy for power generation. The sun, from the outer edge of the Oort cloud, would appear as an extremely bright star rather than as a disk. It would be unambiguously the brightest object in the sky by an enormous margin, but it would not look like the sun as seen from Earth. It would look like a point of intense light in darkness, providing warmth and gravity at a level barely distinguishable from the surrounding stellar environment. The Oort cloud does not merely extend the solar system to uncomfortable distances. It demonstrates that the question of how long it would take humans to reach the edge of the solar system has no single answer, and that some definitions of that edge produce answers so extreme as to render the question academic. If the edge is the outer Oort cloud, the honest answer, using any technology that currently exists, or that physics plausibly permits in the near future, is that humans cannot reach it within a single lifetime. The distance that gravity calls home is simply not the distance that biology can cross. The mathematics of deep space travel is unforgiving, but it is at least consistent. Plug in your velocity, your distance, your propulsion system's efficiency, and the equations return an answer. The answer may be discouraging. It may be measured in decades or centuries, but it is precise, and it does not argue back. Human biology is considerably less cooperative. The equations say nothing about what happens to the crew during the years or decades those calculations describe. They say nothing about bone density, about radiation exposure, about the psychological deterioration that follows prolonged confinement in a pressurized cylinder far from anything familiar. The math describes a trajectory. Biology determines whether anyone arrives intact enough to matter. The most immediate threat to humans in deep space is one that receives less attention than it deserves, because on Earth it is almost entirely invisible. Cosmic radiation permeates the space beyond Earth's protective magnetic field, continuously and from every direction. These are not the relatively gentle energetic particles that Earth's magnetosphere deflects. They are high-energy atomic nuclei stripped of their electrons and accelerated by supernovae and other catastrophic stellar events across thousands of light years before arriving in the outer solar system travelling near the speed of light. Inside Earth's magnetic bubble, this radiation is largely deflected. Aboard the International Space Station, still within the magnetosphere, astronauts receive roughly the same annual radiation dose as a frequent flyer accumulates in decades of air travel. Beyond the magnetosphere, the numbers change fundamentally. A spacecraft bound for the Oort cloud, or even simply crossing the heliopause, moves through an environment where cosmic ray exposure accumulates without relief. Current NASA guidelines limit career radiation exposure for astronauts to levels that translate roughly to a 3% increased lifetime cancer risk. A deep space mission lasting 20 years would exceed those limits many times over using any shielding system practical enough to actually fly. Energetic galactic cosmic rays are particularly difficult to stop because they interact with shielding material in ways that can produce secondary radiation, sometimes making thick shielding counterproductive. A wall of lead stops conventional radiation. A wall of lead bombarded by galactic cosmic rays produces a spray of secondary particles on the other side. The optimal shielding material for cosmic radiation is hydrogen-rich material, essentially water or polyethylene, which absorbs the particles more cleanly. But water is heavy, and mass is the enemy of every propulsion calculation. Solar events introduce a second radiation hazard that is more acute but shorter in duration. A major solar particle event, the kind of energetic proton storm that erupts from the Sun during periods of intense magnetic activity, can deliver a lethal radiation dose within hours without adequate shielding. Earth's magnetic field and atmosphere absorb these storms harmlessly. A spacecraft in the outer solar system has neither protection. Missions would require a heavily shielded storm shelter, a small section of the vessel surrounded by enough material to reduce the dose to survivable levels during the hours or days of peak emission. This shelter adds mass to every mission, regardless of whether the storm ever comes, because the storm cannot be predicted far enough in advance to add protection retroactively. Radiation is invisible and accumulative, damaging DNA in ways that manifest as cancer years or decades after exposure. The deterioration of the skeleton and musculature is more immediate and mechanically obvious. Humans evolved in a gravitational field. Their bones respond to mechanical loading by maintaining density, and when loading disappears, density follows. Astronauts aboard the International Space Station, even following rigorous daily exercise protocols, lose bone mass at rates roughly equivalent to severe osteoporosis. After 6 months in microgravity, bone density in the spine and hips can drop by several percent. Muscle mass follows a similar trajectory. The body reads an environment of weightlessness as permission to reduce the infrastructure that gravity previously required, and it does so with metabolic efficiency that is deeply inconvenient for mission planners. A mission of the durations discussed in previous sections, the decades required to reach the inner Oort cloud, would transform crew members into physiological invalids long before arrival. The standard proposed solution is artificial gravity through rotation, spinning the crew habitat fast enough to press occupants against the outer wall with a force approximating Earth's gravitational pull. This works in principle and violates no physical laws. It also adds structural complexity, requires a rotation radius large enough to avoid the disorienting effects of Coriolis forces, and introduces engineering challenges that every serious study acknowledges without entirely resolving. A habitat that rotates fast enough in a small radius produces a strong enough Coriolis effect that simply walking from one end to the other becomes nauseating. A habitat rotating slowly enough to be comfortable requires a radius of perhaps 100 meters, demanding a spacecraft architecture more structurally elaborate than anything humanity has ever built. Isolation compounds the physiological challenges with psychological ones that are equally real and considerably harder to quantify. Human beings are social animals calibrated for a world where other humans are always nearby, and help is never more than a few minutes away. Submarine crews and Antarctic winter-over teams provide the closest analogues to deep space confinement, and the psychological literature from those environments is sobering. Depression, interpersonal conflict, motivational collapse, and cognitive decline appear with enough regularity that mission planners treat them as engineering constraints rather than personal failings. On a voyage measured in decades, crew selection, social structure, and psychological support systems become as mission-critical as propulsion efficiency. Communication delay makes the psychological burden heavier because it eliminates the one resource that isolated humans have historically relied on most: the ability to reach someone outside. A spacecraft approaching the heliopause is already experiencing communication delays of many hours. A vessel in the Oort cloud would face delays of days. Mission controllers cannot intervene in a crisis. They can only respond long after the moment has passed. Whatever goes wrong, whether it is medical, mechanical, or interpersonal, the crew must handle it with the resources aboard and the knowledge they carried with them when they left. Medical emergencies illuminate this constraint with particular clarity. A burst appendix, a serious infection, a traumatic injury, a psychiatric break requiring sedation or restraint, all of these demand capabilities that current spaceflight medicine does not provide and cannot easily provide within mass and volume constraints that remain acceptable to propulsion engineers. A surgeon aboard a spacecraft is a mass allocation decision. Every kilogram devoted to medical equipment is a kilogram not devoted to fuel, shielding, or food. Every system brought aboard to handle emergencies is a system that requires maintenance, supplies, and expertise that must also be allocated. The further the spacecraft travels, the more complete its medical self-sufficiency must be, and completeness has mass. This is the fundamental difficulty that pure mathematics cannot capture. A calculation that shows a spacecraft reaching the Oort cloud in 30 years at a given velocity is formally correct. It describes a physical trajectory through space. What it does not describe is whether any human being who departs on that trajectory will remain capable, healthy, psychologically coherent, and alive at the end of it. The engineering problem of propulsion is difficult but tractable. The biology problem is difficult and deeply resistant to simple solutions. Before distance becomes the limitation, survivability may already have become the answer. If human biology sets the ceiling on what a crew can endure, propulsion sets the floor on how long they must endure it. These two constraints press against each other from opposite directions, and the answer to the question of whether humans can ever meaningfully reach the outer solar system depends entirely on whether engineering can close the gap between them. The previous sections established what current technology produces in terms of travel time. The picture was not encouraging. Reaching the heliopause takes decades. Reaching the Oort cloud takes centuries. The question now is whether propulsion concepts beyond chemical rockets could change those numbers enough to matter. Chemical propulsion is where the conversation must begin, because it is what humanity has actually built and flown. The fundamental limitation is not a design flaw awaiting correction, it is thermodynamic. Burning chemical propellants releases energy determined by the molecular bonds being broken and reformed. Those bonds contain a fixed amount of energy regardless of how cleverly the engine is arranged. The exhaust velocity, which is the quantity that ultimately determines how fast a rocket can push a spacecraft, is bounded by the energy available in the propellant. The best chemical engines achieve exhaust velocities around 4 to 5 kilometers per second. This translates to spacecraft velocities of perhaps 20 kilometers per second for realistically proportioned missions. Against the distances involved in reaching even the heliopause at 120 astronomical units, this produces journey times measured in decades even before accounting for deceleration. Chemical propulsion is not a candidate for shortening the journey in any meaningful sense. It is the baseline against which everything else is measured. Nuclear thermal propulsion takes the same basic rocket architecture and replaces the chemical reaction with a nuclear reactor heating propellant to much higher temperatures before expelling it. The exhaust velocity roughly doubles compared to chemical engines, reaching 8 to 10 kilometers per second in the designs NASA studied seriously during Project Nerva in the 1960s and 1970s. Doubling exhaust velocity does not simply double spacecraft velocity due to the rocket equation's exponential relationship between mass ratio and final speed, but it meaningfully reduces propellant requirements for a given mission or allows higher final velocities for the same propellant mass. A nuclear thermal spacecraft could potentially reach the heliopause in 30 to 40 years rather than 50, a genuine improvement but not a transformation. The trade-offs involve reactor mass, radiation shielding required to protect crew from the reactor itself, and the political complications surrounding launching nuclear reactors from Earth's surface. The physics is sound, the engineering largely understood. The barriers are institutional as much as technical. Nuclear electric propulsion decouples the reactor from the propellant entirely. A nuclear reactor generates electricity, which then drives an ion engine or similar device that accelerates propellant electromagnetically rather than thermally. Ion engines achieve exhaust velocities 10 to 50 times greater than chemical rockets, which sounds revolutionary until you realize they produce extremely low thrust. The acceleration is measured in milligrams rather than kilograms of force. Nuclear electric systems excel at very long missions where continuous low-level thrust accumulates over years into impressive final velocities, but the thrust levels make them poorly suited for quickly escaping the inner solar system or decelerating on arrival. For human missions to the deep outer solar system, nuclear electric propulsion remains a component of a hybrid approach rather than a complete solution on its own. Fusion propulsion is where the numbers begin shifting dramatically. If controlled fusion can be achieved with sufficient efficiency to drive a spacecraft, the energy density exceeds fission by roughly a factor of 4, and exhaust velocities could reach percentages of light speed rather than fractions of a percent. A fusion-driven spacecraft accelerating continuously at comfortable levels could potentially reach the heliopause in 2 to 3 years rather than decades. The Oort cloud's inner edge becomes a journey of decades rather than centuries. The entire character of the outer solar system changes from unreachable to merely distant. The difficulty is that controlled fusion has been approaching practical realization for most of the past 70 years without quite arriving. Private fusion ventures have accelerated progress, and the physics is not in doubt. Whether fusion drives capable of powering spacecraft will exist within the coming century is genuinely uncertain rather than clearly impossible. Beam-driven propulsion concepts take a different approach entirely, leaving the energy source behind rather than carrying it aboard. A powerful laser or microwave beam directed from a fixed installation, perhaps in the inner solar system, pushes a lightweight reflective sail attached to the spacecraft. The advantage is immediate. You're not accelerating your fuel, only your payload. The disadvantage is equally immediate. Once you stop accelerating, you cannot decelerate using the beam, because the installation is now behind you moving away. For robotic probes, this one-way limitation matters less. For human missions requiring arrival and return, beam-driven concepts require combining a sail for outbound acceleration with some other system for braking. Laser sail concepts could theoretically push a small payload to meaningful fractions of light speed. For heavy human-rated spacecraft, the power requirements become extraordinary. A laser powerful enough to accelerate a crewed vessel to useful velocities would represent an energy installation dwarfing anything humanity has ever constructed. What all of these concepts share is that higher performance always brings real trade-offs. Fusion plants are massive and complex. Nuclear systems require radiation management that adds mass and engineering overhead. Beam systems require infrastructure that does not yet exist. No propulsion concept advances spacecraft velocity for free. Every increase in speed arrives with increased system complexity, increased power requirements, increased heat rejection demands, and frequently increased danger to the crew from radiation or component failure. The outer solar system does not become close under any physics-respecting propulsion scenario. What changes is the degree of difficulty. The heliopause that requires 50 years by chemical propulsion might require 5 years by fusion drive. 5 years is manageable for human biology in ways that 50 years is not. The Oort cloud's inner boundary that requires centuries chemically might require decades by fusion. Decades remain challenging. They do not become easy. This is the critical distinction between propulsion concepts grounded in verified physics and the faster-than-light concepts that appear in fiction. Warp drives, wormholes, and hyperspace tunnels are not propulsion technologies awaiting engineering development. They are either mathematically speculative in ways requiring exotic matter with properties no experiment has confirmed, or they are storytelling devices with no physical basis at all. The technologies described here, nuclear, fusion, beam-driven, are grounded in physics that works in laboratories today. The engineering challenges are real, and in some cases severe, but none of them violates established physical law. The outer solar system could become reachable within human lifetimes using these approaches, if civilization commits the resources and time to develop them. What they cannot deliver is a shortcut that makes distance stop mattering. The edge of the solar system remains genuinely far under any scenario that respects the physics we actually understand. If propulsion cannot close the gap within a single human lifetime, a different kind of solution emerges. Not a faster ship, but a different relationship between the ship and the people aboard it. The generation ship concept treats extreme travel time not as a problem to be solved, but as a condition to be accommodated. Rather than asking how to make the journey short enough for one person to complete, it asks how to make the journey sustainable across multiple human lifetimes. This is not a science fiction fantasy. It is a practical engineering response to a genuine constraint, and it deserves examination with the same rigor applied to propulsion concepts or biological limitations. The basic architecture of a generation ship follows from the requirements. If a journey takes 200 years, no individual alive at departure will be alive at arrival. The mission therefore requires a self-sustaining human community, capable of maintaining itself, reproducing, educating successive generations, and preserving both technical knowledge and mission purpose across time spans longer than any institution humanity has ever successfully maintained. The vessel must be simultaneously a spacecraft, a habitat, an ecosystem, a school, a hospital, a society, and a civilization in miniature. The engineering scale this demands is enormous. Food production must be internal and continuous, which means agriculture under artificial light, which means significant power consumption and significant volume. Water must cycle through biological and mechanical systems indefinitely without net loss. Air must be maintained within narrow tolerances of composition and pressure. Medicine must be practiced without resupply. Equipment must be repaired and eventually manufactured from aboard the ship, because replacement parts cannot arrive from Earth within any useful time frame once the vessel is years from home. Estimates for a generation ship capable of housing a genuinely self-sustaining community range from tens of thousands to hundreds of thousands of people. Smaller populations face extinction risks from disease, accident, or simple genetic bottlenecks as successive generations reduce diversity. A population of a few hundred would likely experience genetic drift severe enough to cause problems within 5 or 6 generations. Several thousand people represents a rough minimum for long-term biological viability, and that minimum assumes careful management of reproduction to maintain genetic diversity. The physical structure required to house, feed, and sustain several thousand people across centuries would be measured in millions of tons. The energy to move such a structure through the outer solar system at any meaningful velocity exceeds anything chemical propulsion could plausibly deliver. A generation ship is therefore not separable from the propulsion problem. It makes that problem dramatically harder. The ethical dimensions are genuine and cannot be dismissed as merely philosophical. Every person born aboard a generation ship during its transit is a person who never consented to the mission, never had the option to decline, and may die before reaching the destination their great-grandparents set out for. They exist entirely within the context of the ship. Their choices about vocation, partnership, reproduction, and meaning all occur within constraints established by people generations before them. Whether this constitutes an ethical violation depends on how one weighs autonomy against the circumstances of birth, and humans have never resolved that question cleanly even in terrestrial contexts. But the generation ship makes the question impossible to avoid. The founders choose not only for themselves, but for every descendant the mission will produce, across a time span none of them can fully anticipate. Governance structures established at departure may become oppressive or dysfunctional over generations. Rebellions, schisms, or simple institutional decay could derail the mission entirely before arrival. Human societies do not maintain stable purpose across 2 centuries without extraordinary effort, and no earthbound institution has ever faced comparable isolation. Suspended animation offers a conceptually cleaner solution to the time problem, if it can be achieved. A crew that sleeps through the journey does not age meaningfully, does not require calories or social structure during transit, does not produce children who inherit an unwanted mission, and arrives at the destination as the same individuals who departed. The ethical complications largely dissolve. The engineering complications remain severe but are different in character. No human has ever been successfully suspended for more than a few hours in medically relevant contexts. Deep cooling sufficient to halt biological processes for decades risks ice crystal formation in tissues, membrane damage from extended stasis, and metabolic processes that cannot simply be switched off and on like a machine. Research into suspended animation is ongoing, and results are not zero, but the gap between current capability and decades-long stasis is vast. It may prove bridgeable. It has not yet been bridged. The embryo ship concept represents a third approach that sidesteps both generational ethics and suspension technology by carrying not adults but genetic material. A vessel bearing frozen embryos or genetic samples, tended by automated systems throughout transit, would arrive at the destination and initiate biological development, using artificial gestation and robotic caregiving. The first humans at the destination would be born there, raised by machines, with no memory of Earth and no experience of the journey. The practical barriers are significant. Raising psychologically healthy humans requires social interaction, attachment, and complexity that no robotic system has yet demonstrated. The ethical questions shift rather than disappear, creating humans in isolation, dependent entirely on automated systems, without community or culture beyond whatever can be programmed, raises concerns that differ from those surrounding generation ships, but are equally genuine. What all 3 approaches share is that they relocate the problem rather than solve it. A generation ship answers the biological constraint of human lifespan by distributing the journey across many lives. It does not answer the engineering challenge of building and moving a structure massive enough to sustain those lives, and it introduces sociological and ethical complexity that may prove more intractable than the propulsion problem. Suspended animation answers the biological constraint directly, but requires medical technology that does not exist. Embryo ships sidestep the constraint by abandoning the original crew entirely, producing an outcome in which the people who arrive bear no personal continuity with the people who chose to go. Whether any of these approaches represents the only realistic human option depends entirely on which boundary of the solar system we are attempting to reach. For the heliopause at 120 astronomical units, a generation ship is not necessary if propulsion technology continues developing. Fusion drives or advanced nuclear systems could potentially deliver a crew within years rather than centuries. The Kuiper Belt is closer still. These destinations are within reach of single lifetime missions under plausible propulsion scenarios. The mathematics do not demand multi-generational solutions for the inner boundary questions. For the Oort cloud, the picture changes completely. The inner Oort cloud begins at perhaps 2,000 astronomical units. The outer boundary may extend to 100,000 astronomical units or beyond. No propulsion concept rooted in verified physics and near-term engineering can deliver a human crew to those distances and back within a single lifetime. The generation ship, for all its complications, may genuinely represent the only framework within which humans could reach those destinations at all. The question is whether reaching the Oort cloud qualifies as a meaningful human goal, given what the journey would cost in resources, ethics, and institutional coherence across centuries. The answer to that question is not a physics problem. It is a question about what humanity decides it values and what scale of commitment it is willing to make. Every estimate of travel time to the edge of the solar system contains a quiet assumption buried inside the arithmetic. The calculation divides distance by velocity, produces a number, and presents that number as an answer. What it rarely acknowledges is that arriving at a location and arriving in any useful sense are entirely different achievements. Reaching the heliopause, the Kuiper Belt, or the Oort cloud as a blur of metal passing through at interplanetary velocity is not the same as being there. The stopping problem transforms the nature of every mission concept, and it deserves the same careful attention that departure velocity and travel duration typically receive. Consider what deep space offers in terms of braking options. Near Earth, a spacecraft can shed velocity through atmospheric drag, spiraling through successive passes and trading kinetic energy for heat without burning a drop of propellant. Near Jupiter or Saturn, a spacecraft can swing around a massive planet and use gravitational geometry to bleed speed, arriving at a lower velocity than it possessed on approach. The outer solar system offers neither option. The heliopause sits in a region of space so remote that the nearest planetary mass capable of providing meaningful gravitational assistance is billions of kilometers behind the spacecraft. The interstellar medium provides negligible resistance. There is no atmosphere, no convenient gravity well, nothing except the spacecraft's own propulsion system standing between arrival velocity and perpetual outbound drift. This means that any mission intending to stop must carry enough propellant to stop. The rocket equation, which governs how velocity and fuel mass relate to each other, does not care about the direction of travel. Decelerating from a given velocity requires exactly as much energy as accelerating to that velocity in the first place. A spacecraft that burns enormous quantities of propellant reaching the heliopause must carry additional propellant to arrest that same velocity on arrival. The mass of fuel required for deceleration must itself be carried and accelerated during the outbound journey, which requires yet more fuel, which itself adds mass, which requires yet more fuel still. The compounding works against every mission designer trying to achieve a controlled arrival at extreme distances. The practical consequence is that deceleration does not simply double mission fuel requirements. It more than doubles them, often dramatically, because the deceleration fuel must ride along for the entire outbound leg as dead weight. Engineers working on ambitious deep space concepts sometimes describe this as the tyranny of the rocket equation, a phrase that captures both the mathematical elegance of the relationship and its merciless implications for mission feasibility. Adding a stopping requirement to a mission that barely closes on propellant budget as a one-way proposition can render that mission impossible under the same propulsion assumptions. This explains why most serious proposals for reaching the outer solar system in any reasonable time frame describe flyby architectures rather than rendezvous or orbital insertion. A flyby mission accepts that the spacecraft will pass through the target region at high velocity, gathering data during a window measured in hours or days before continuing outbound. The Voyager probes operate on exactly this principle. They flew past Jupiter, Saturn, Uranus and Neptune without slowing, collecting observations during close approach and then continuing on trajectories that will carry them beyond the solar system entirely. They never had the option of stopping. Their missions were designed around the understanding that stopping was not achievable within their propellant budgets. A flyby of the heliopause or the inner Oort cloud would look similar. A spacecraft optimized for high transit velocity arrives, observes, transmits, and continues. From a scientific standpoint, this produces genuine value. Measurements of the local plasma environment, magnetic field configuration, particle populations, and dust density would answer questions that remain open decades after the Voyager crossings. But from the standpoint of human presence, a flyby is categorically different from arrival. Humans cannot conduct science through a window they pass in an afternoon. A crude flyby of the outer solar system would expose a crew to years of radiation and confinement for a brief transit through a region they could not meaningfully inhabit, sample, or study at the pace human investigation requires. Rendezvous missions, where a spacecraft matches velocity with a target and enters a stable orbit or hovers nearby, demand propellant budgets that currently exceed any realistic launch mass. Orbital insertion around a body in the Kuiper belt requires not just slowing from interplanetary velocities, but matching the orbital parameters of an object moving in a specific direction at specific speed. Settlement concepts require even more. A habitat must be delivered, assembled, supplied, and maintained in a location where resupply from Earth takes years to arrive. The energy accounting for any of these scenarios pushes well beyond what current or near-term propulsion technology can support at distances beyond Neptune. The stopping problem also reframes what counts as mission success. If a spacecraft cannot stop, success means data returned before the flyby window closes. If the communication lag between Earth and the outer solar system already stretches to hours, a crewed mission adds the complexity of human decision-making in an environment where ground support cannot respond in real time. Instructions sent from Earth during a crisis at the heliopause would arrive long after any situation had resolved itself one way or another. The crew would be operationally autonomous in ways that exceed anything experienced by astronauts in Earth orbit or even on the lunar surface. Many travel time estimates circulating in popular discussions of solar system exploration omit these complications entirely. They calculate transit duration under optimistic propulsion assumptions and present the result as though arrival were equivalent to success. The numbers are not wrong. The framing is incomplete. A journey whose endpoint is a controlled, productive human presence at the boundary of the solar system is a fundamentally more demanding undertaking than a journey whose endpoint is simply crossing a line on a map while moving too fast to stop. This does not make such missions impossible in principle. It means that mission architecture cannot treat propulsion and deceleration as separable problems. Every velocity gained during the outbound leg is a velocity that must eventually be managed on arrival. Clever mission designs might exploit solar gravity at departure, use tethers or electromagnetic braking in regions where the interplanetary medium is dense enough to provide some resistance, or rely on propulsion systems capable of very high efficiency over long burn durations. None of these solutions are simple, none of them come free, and none of them change the underlying physics that make stopping at the edge of the solar system almost as difficult as reaching it in the first place. Everything examined across this discussion has been building toward a single practical reckoning. The question of how long it would take humans to reach the edge of the solar system does not have one answer. It has several answers, each dependent on which edge you mean, which propulsion technology you assume, and what kind of mission you consider success. Laying those answers side by side, clearly and honestly, reveals something important about the scale of the challenge and the limits of what the word reachable actually means. Start with the destinations closest to Earth and work outward. The outer planets, Jupiter through Neptune, represent the solar system's inner suburbs by the standards of this discussion. Under current human-rated technology, meaning chemical propulsion systems comparable to those used in the Apollo era and the Space Launch System, a crewed mission to Jupiter requires roughly 2 years of transit each way under optimal trajectory conditions. Saturn adds another year. Uranus and Neptune push total mission durations past a decade when you account for deceleration, orbital operations, and return. These timelines are uncomfortable, but not biologically impossible. With advanced nuclear thermal propulsion, transit times compress by a factor of 2 to 3. A crewed Jupiter mission becomes plausible within 3 to 4 years round trip. Neptune becomes a genuine multi-year deep space expedition rather than a generational commitment. Under far future propulsion assumptions involving nuclear pulse systems or fusion drives, the outer planets become accessible on timescales comparable to a long submarine deployment. Challenging, demanding enormous life support infrastructure, but achievable within a single human career. The Kuiper Belt, extending from roughly 30 to 50 astronomical units, is the first destination where the word reachable begins to strain. Under chemical propulsion, a one-way transit to the inner Kuiper Belt takes approximately 20 to 30 years, assuming no deceleration and a trajectory optimized purely for velocity. A flyby mission carrying human beings for 3 decades of confinement and radiation exposure approaches the outer edge of biological tolerability, though it remains technically within a human lifetime. A mission requiring controlled arrival, meaning the spacecraft must decelerate and achieve any form of stable presence, becomes extraordinarily difficult under chemical propulsion because the deceleration fuel mass overwhelms any plausible launch configuration. Nuclear thermal propulsion improves transit time but does not resolve the deceleration problem without enormous mass penalties. Advanced nuclear pulse propulsion or fusion systems could in principle deliver a crewed rendezvous mission to the Kuiper Belt within 15 to 20 years of elapsed mission time, which represents a realistic if brutal career commitment for crew members who depart in early adulthood. The Kuiper Belt sits at the edge of what might be considered reachable within a single lifetime under optimistic but physically grounded propulsion assumptions, provided the mission accepts one-way or flyby architecture. A mission requiring round-trip crewed presence at Kuiper Belt, distances under any propulsion system available within the next century, pushes past what normal human lifespan comfortably accommodates. The heliopause, sitting somewhere between 120 and 160 astronomical units depending on solar wind conditions, is where the arithmetic becomes genuinely punishing. Voyager 1 took approximately 35 years to cross this boundary under unpowered drift following its planetary flybys. A mission optimized for the heliopause rather than planetary encounters and equipped with nuclear electric propulsion might reach that boundary in 20 to 25 years. Advanced nuclear pulse concepts like Project Orion derivatives could potentially close the distance in 10 to 15 years. Even under those favourable assumptions, a crewed mission designed to achieve any form of productive presence at the heliopause, rather than a brief flyby transit, requires life support, radiation shielding, and closed-loop life systems that represent their own unsolved engineering problems. The heliopause is reachable within a human lifetime under advanced propulsion assumptions, but only barely, only as a one-way or flyby mission under current technology trajectories, and only at enormous cost in crew health and mission complexity. The Oort cloud renders all of these considerations abstract. The inner edge of the Oort cloud begins at roughly 2,000 astronomical units and extends to perhaps 100,000 astronomical units or more. Even at the velocities achievable by the most ambitious propulsion concepts seriously proposed using known physics, reaching the inner Oort cloud requires centuries. Nuclear pulse propulsion at its most optimistic performance might cover 2,000 astronomical units in something approaching 50 to 70 years under continuous thrust, which already demands either a very long human life or a crew that accepts dying before arrival. The outer Oort cloud under any propulsion system grounded in current physics is not reachable within a human lifetime under any mission architecture. It is not even close. It belongs to a category of destinations that requires either technology we cannot currently describe in engineering terms, mission concepts that abandon the idea of individual human travelers in favor of generational continuity, or timescales that are human only in a civilizational rather than biological sense. The mission architecture question cuts across all of these destinations. A crewed flyby requires less propellant than a rendezvous mission. A one-way expedition requires less propellant than a round trip. A robotic precursor can gather data that a crewed mission would otherwise need to collect at enormous cost in life support and risk. Mapping these variables onto each destination produces a matrix of possibilities rather than a single threshold. The Kuiper Belt might be reachable for a one-way human expedition under near-future nuclear propulsion. It is not reachable for a crewed round trip under the same assumptions. The heliopause might be crossable in a flyby under advanced propulsion. Establishing any human presence there that lasts longer than a few days of closest approach is a different mission entirely, demanding capabilities that do not yet exist. For practical purposes, the most defensible definition of the solar system's edge in any discussion of human travel is the heliopause. It represents the first genuine physical boundary, the point where the sun's direct influence gives way to interstellar space. It is measurable, it has been crossed instrumentally, and it corresponds to something physically meaningful rather than an arbitrary distance threshold. The Oort cloud is technically part of the solar system in the sense that comets originating there remain gravitationally bound to the sun. But a boundary defined by objects we have never directly observed, spanning distances that dwarf anything humanity has ever traversed, functions less as an edge and more as an abstraction. Under that practical definition, the answer to the original question is this: reaching the edge of the solar system in any meaningful human sense, not merely launching a probe that will eventually drift across a line decades hence, but sending human beings to the heliopause and returning them alive, requires propulsion technology that does not currently exist in operational form, mission durations measured in decades rather than years, life support systems that have never been tested at the required duration, and a tolerance for radiation exposure that pushes against the outer limits of what biology permits. It is not impossible. The physics does not forbid it. But the gap between where humanity stands today and what such a mission demands is not a gap that closes with incremental improvement. It requires a transformation in what human spaceflight is capable of building, sustaining, and surviving. The question asked at the beginning of this discussion seems straightforward. How long would it actually take humans to reach the edge of the solar system? The answer, after working through every layer of what that question contains, is that the edge was never a fixed coordinate. It was always a mirror, reflecting back whatever assumptions you brought to it. Define the edge as the heliopause, and the answer is decades under any propulsion system currently in service, possibly compressed to 15 or 20 years under nuclear systems that exist in theory but not in hardware, and still requiring mission architecture and crew survivability solutions that have never been demonstrated at the necessary scale. Define the edge as the Kuiper Belt's outer boundary, and the answer shifts. Define it as the Oort cloud, and the arithmetic does not produce a human travel time at all. It produces a civilizational timescale, a number that has meaning only if you are thinking in terms of generations rather than careers or lifetimes. This ambiguity is not a failure of the question. It is the most honest answer the question can yield. What the exploration of these distances does reveal clearly is the widening gap between what robotic probes can reach and what human beings can survive reaching. Voyager 1 crossed the heliopause because it did not need food, sleep, radiation shielding scaled for biology, or a return ticket. It required no deceleration because arriving slowly was irrelevant. It carries instruments that can fail and go unreplaced, systems that can degrade over decades without killing anyone. The probe's crossing of the heliopause 46 years after launch was a genuine scientific landmark, but it tells us almost nothing about the feasibility of sending people to that same boundary and bringing them home. Robotic missions can cross meaningful thresholds on timescales that would destroy human travelers under identical conditions. The distinction between what a machine can endure and what a body can endure defines the boundary of the possible more sharply than any propulsion equation. Human travel carries constraints that have nothing to do with distance and everything to do with survival. The body requires continuous caloric input across decades of transit. Bone density decreases under microgravity in ways that compound over years. Cosmic radiation penetrates spacecraft walls and accumulates in tissue over timescales that chemical propulsion would demand. Psychological coherence in extreme isolation over multi-decade missions has no tested baseline. Stopping at the destination requires as much fuel as getting there. None of these problems are insurmountable in principle, but none of them are solved in practice, and every one of them adds mass, complexity, and failure probability to a mission that already demands more from propulsion than any existing system can provide. Within all of this, there are destinations that fit inside a human life, and destinations that do not. The outer planets are hard but conceivable under propulsion systems that could exist within decades. The Kuiper Belt sits at the edge of what one human lifetime can contain, just barely within reach on a one-way flyby under optimistic assumptions, just beyond reach on a round trip under any near-term technology. The heliopause is reachable in concept, unreachable in practice with current tools. The Oort cloud is not a destination for individual humans. It is a destination for whatever human civilization might eventually become, if it becomes anything at all beyond what it is now. What this reveals is something larger than a travel time estimate. The solar system is simultaneously our neighbourhood and an almost unfathomably large frontier. From the Sun to Neptune spans 40 astronomical units, a distance that took our fastest probes decades to cross. From the Sun to the inner Oort cloud spans 50 times farther still. From the Sun to the outer edge of the Oort cloud spans a distance that dwarfs the gap to our nearest stellar neighbour. The entire star system humanity has called home since the species emerged is, by any honest reckoning, vast beyond intuitive comprehension. The planets we can see with the naked eye represent a tiny central fraction of the total structure. The regions beyond them are so remote that we have never visited them, even instrumentally, except at the outermost edge of what our earliest launched probes are still only now approaching. Future technology will move the boundary of what is reachable. Propulsion concepts that seem speculative today may become engineering realities within a century. What the physics does not permit is erasing the scale entirely. Faster travel compresses the timelines, but does not eliminate the distances. Better life support extends crew survivability, but does not eliminate the years. The solar system will remain large even when humanity is faster, and the edge will remain a test of what the word reachable is actually willing to mean.